Hi folks, in this lesson we're going to be looking at forces for the higher physics course, and we're going to start by looking, as always, at the learning outcomes. So we can see in the Our Dynamic Universe course notes booklet that if we look at the section on forces, energy and power, now the first thing to note is that all of these formulas that you're seeing here, they're not new. We covered these in National 5 Physics, and indeed there are no formulas in this section, no new formulas in this section, although what we will do is we'll apply the Newton's laws and the associated formulas in different ways. We'll try and make it as complicated as possible for you, is how it seems. But looking at this, it says that we're going to use vector addition and appropriate relationships to solve problems involving balanced and unbalanced forces, mass and acceleration, and gravitational field strength. So let's break this down a little bit. Vector addition, specifically what we're going to do in this lesson is we're going to look at vector addition only in one plane. So that will be a horizontal plane or a vertical plane. Resolving the forces from that is as easy as adding or subtracting them. Knowledge of the effects of friction on a moving object, with no reference to this. Well, friction will always act against the motion of an object, or act against the force causing the motion of an object. Explanation, well, we're not going to look at terminal velocity, so these two we'll do in another lesson. Use of Newton's first and second laws to explain the motion of an object. Free body diagrams, yes, involving friction and tension. Now we've looked at friction a bit before, but we haven't come really across tension, and there'll be quite a bit of work in looking at tension in this section here. And then the vector components in 2 dimensions, that's something that we'll do in the next lesson. Okay, so really what we're going to do, we'll jump straight in and we'll look at Newton's laws again. So laws haven't changed since National 5. We'll still have Newton's first law as an object will remain at rest or a constant speed unless acted upon by an unbalanced force. Newton's second law, if it is acted upon by an unbalanced force, the object will accelerate in the direction of that unbalanced force. And Newton's third law, for every action there is an equal and opposite reaction. Now there's some examples in the course notes that you can see just here, but we can talk a little bit more about them, and I'll give you a couple of extra worked examples just now. So as an example of Newton's first law, if we have an object and there's no forces acting on it, it's not going to move, so we would have velocity is equal to 0 meters per second. We could have the same object, and we could be applying, for example, a 10 Newton force acting either side. Now again, if it's not moving, velocity is still going to be 0. If, on the other hand, we have an object that is already moving with a velocity, we know at that point then the forces must be balanced. Now, it doesn't just need to be an equal pairing. We could have 2 Newton force, we could say of air resistance, and a 5 Newton force of ground friction or surface friction, and we would know that our driving force must be, if it's traveling at a constant speed, the forces must be balanced, and so 2 plus 5 would be equal to 7 newtons. So again, forces are balanced. They're all in the horizontal plane, but the net force is equal to 0 in every case of these. So that's for Newton's first law. For Newton's second law, well, if we just look at this object above, you could have a similar 2 Newton force, 5 Newton force, but you could increase the driving force here, and if we say we're going to increase it to 20 newtons. Now if we knew the mass of the object, let's say that the mass is 3 kilograms, then we can work out an acceleration. We have F equals ma. Now, quite often at National 5, I laboured the point that this F, we have three forces here, but which F do you use? And so, really what we're talking about is the unbalanced force. You must resolve all your force vectors first before actually applying it into this formula. So we'll have our 7 on one side, or 20 on the other side. That's going to give our 13 Newton unbalanced force. Force is a vector, so we're going to say to the right. And then if we want to work out an acceleration, A is equal to F over m. We're going to have 13 over 3, which gives us 4.3 meters per second squared. And Newton's third law, a typical example of Newton's third law, we could have a cat. It's obviously a cat. Cat sitting on a stool. If the cat has a mass of, I don't know what the mass of a cat is, say it's 5 kilograms. Seems like quite a fat cat, but maybe not. 5 kilogram cat sitting on a stool. So first of all, what force does the cat apply to the stool? Well, the cat must apply its weight, W equals mg, so we're going to have 5 times 9.8, which will give 49 newtons. So the cat is applying a 49 newton force onto the stool. The reaction force, or according to Newton's third law, for every action there's an equal and opposite reaction. Because the cat is stationary, it's not moving, the stool must be applying a 49 newton reaction force to the weight applied to it. And so that's a very basic rundown of the Newton's three laws. Moving on, we have, this is on page 20 of the course notes, we have some worked examples, and these are examples involving pulleys, and we're looking at now tension in the pulley cords. So we have a scenario here where we have two unequal masses. Now common sense would dictate that this is the smaller mass, and so this is going to accelerate upwards and this is going to be accelerating downwards. And so the overall motion is going to be coming up here, down here. This is going to accelerate down this way. Now the force that's acting on this is going to be its weight, so that's going to be 3 times 9.8, you're going to have 29.4 newtons, and the weight acting on this is going to be 88.2 newtons, again 9 times 9.8. Now if we're actually looking, although this is moving up, that's moving down, what this is doing is if you took this away altogether, then the acceleration of this 9 kilogram mass is just going to be purely caused by this. But because there's sort of a counterbalance here, the acceleration has to be slightly less, and that's because these forces, although they're both acting down, the way that this is moving up, and so this is causing, this is acting against the force pulling that. This here is pulling this cord. Now as this cord is coming down here, because the motion is down in that direction, actually a motion up is going to oppose that arrow. You can see the arrows are in two different directions. So what we're going to do, we'll subtract the two forces. So this is the weight of the 9 kilogram object and the weight of the 3 kilogram object, and you'll get an overall unbalanced force. So we can say that Fun there is 58.8 newtons. Now, this is crucial with all these kind of tension problems. It's one system, that the whole thing is going to be getting accelerated. It's going to be harder to move. If you imagine that, for example, that it's not attached to a pulley, and you have your 9 kilogram mass here, and you pull that along with a string and with whatever force. And so say you use 58.8 newtons, and so you pull it along with that. If you attach another string, and this is a 3 kilogram mass, and pull it with the same force, this is obviously a lot harder to move than just the 9 kilogram mass on its own. And so we do have to take into consideration the whole system. The whole thing is moving. At no point ever the line will ever go slack. And so we can treat it as sort of one rigid body that's moving, although you've got a string which can bend. It is one unit that we're going to treat it as in this case. And so hence we're going to call it 12 kilograms, or the 9 plus 3 will get 12 kilograms. And so our unbalanced force is going to have to accelerate 12 kilograms, because if this accelerates, well, this accelerates downwards at 4.9 meters per second squared. That's going down at 4.9 meters per second squared. This is going up at 4.9 meters per second squared. And so it's one system, and you'll have to treat it as such. You find the unbalanced force and then apply that to the whole mass of the object, both objects. Again, now we have something slightly different here, that both pulleys or both masses are not freely hanging. Now the weight of this is going to act straight down into the table. You're then going to get your balanced reaction force from the table up there. So the weight of that, the net unbalanced force caused by the weight, is going to be 0. And if it's a frictionless surface, that won't affect anything at all. So the only accelerating force in this, the force there is already balanced, so the only accelerating force in this is going to be from the 3 kilogram mass, and that's just going to be 3 times 9.8. You're going to have 29.4. So here, 29.4. This force is pulling the two masses, so it's pulling 12 kilograms. Again, so we're going to work at that. We'll have 2.45 meters per second squared. Now, the tension in the string. If this is accelerating, this whole system, this whole thing, 2.45 meters per second squared, it needs to apply a force of 29.4 newtons to make that accelerate and that accelerate. Okay? But what force is needed to make a 9 kilogram mass accelerate at that? And that's how we work out the tension at this point here. So the tension there, we have an acceleration in that direction of 2.45 meters per second squared. We want to know what force causes this object to accelerate at that in this direction. And with that, so we're only going to use the 9 kilogram mass in this case. So we have 9 times that acceleration, which will be 22.05. Another way to look at tensions is if you imagine, and this will probably explain something around the differences in tension between the strings. If you you've got a ceiling, and onto the ceiling you attach, and this is actually an experiment that you can do. So you attach a Newton balance, which will measure the force, and on that you attach, say, a 1 kilogram mass. Or if let's just say 100 gram mass. And I'm just going to assume for ease that G is 10, and so this is going to give me a force of 1 Newton. And so right now, at this point, there's a tension of 1 Newton, that this together is going to be 100 grams. Now if we attach another string to it, but nothing on it, then the tension in that string is going to be 0. So we've got a 1 Newton tension here, we've got 0 tension here, but if we attach another Newton balance with another mass that's exactly the same, then the tension in this string here is going to be 1 Newton, and the tension in this string must be 2 Newtons. Because up here, this string has got to support 200 grams, and so 200 grams times 10 in our case would be 2 Newtons. this string only has to support the weight of 1. And we can keep going with this. So that now the string on here, which is unloaded, is going to be 0 newtons. Then we're going to have 1 newton, 2 newtons, 3 newtons, and 4 newtons. And so you can see that although they're all attached to each other, the tension gets the tension gets greater and greater as more and more mass is added to it. And that's a similar thing if we look at the next question in our notes. Although this is now, rather than vertically, this is horizontally, here the accelerating force is coming this way. And so at this point, the tension in this string is going to accelerate that, that, and that. Whereas in here, the tension has only got to accelerate that and that. And here, tension has only got to accelerate that. Okay, so if we want to find the acceleration of the 3 trucks, well, 1.8 newtons is pulling 3, or 0.3 plus 0.3 plus 0.3, so 0.9 kilograms. So unbalanced force, we're going to have 1.8 newtons pulling 0.9 kilograms, and that's going to give us an acceleration of 2 meters per second squared. Forget about that now. The tension in the string, this is accelerating. Whatever force, we need a force that would cause 0.6 kilograms to accelerate at 2 meters per second squared. And so we're going to have 0.6 times 2, we're going to have 1.2 newtons. And finally, forget about the rest of them. Now, what acceleration would cause a mass of 0.3 kilograms, or sorry, what force would cause an acceleration of 2 meters per second squared to a mass of 0.3 kilograms, and that would be 0.6 newtons there. And so you work out the initial acceleration of the whole system by taking total mass and using total force. And then you can use the acceleration and the total mass to find out the individual forces, which we're going to call the tensions. Okay, from this point, if we continue with the course notes, the next thing we come to is something called forces and lifts, and I'll do a completely separate video to this where I can go through this in much more detail than I'll have time for just now. So we're going to skip forces and lifts for now, and the next thing you have after that are some practice problems. You can do all of these, so it's 1, 2, 5, 6, 7. You can do 1 to 8, and that should be the next thing that you do. That should keep you going for a period or so. Okay, a very special application of Newton's laws would be forces and lifts. Now this is something that we can do, we can simulate in any lift. All you need is a set of bathroom scales and you can see what's going on. But also, what I want you to do is to try and use your own personal experience of being in a lift. Imagine that you have a lift here, you're standing inside lift, and if the lift is going up, so as the lift first starts to go up, initially it will start to accelerate upwards, and you know when you push the button in the lift and you start to move up, you feel a bit heavier, you feel funny, you feel heavier than you normally are. If you feel heavier, tension is bigger. So the tension goes up of the lift from what it was before, when it was just holding the lift dangling in free space. As the lift reaches its constant velocity, the acceleration goes away, you feel normal again, the tension just goes back to a normal pre-movement state. And then as the lift nears the top of its journey, you feel a bit lighter, that's because the tension must get less, and that is because it's starting to decelerate, it's slowing down. And exactly the opposite happens if you're in a lift that's starting to travel downwards. So as you first start to move, it accelerates downwards. As it accelerates downwards, you feel a bit lighter, and that is because the tension is getting less. When it starts to move at a constant speed, there is no acceleration, and therefore the tension is normal again. And as it gets down to the bottom, the acceleration is going to be in the opposite direction again from the motion, and so that's going to make you feel a bit heavier. The tension increases. And so you can't go far wrong when working out these problems if you just try and remember, try and think about, well, do I feel lighter? Do I feel heavier? If I feel heavier, it's because whatever is happening. If you feel heavier, the tension in the cable is going to be greater. If you feel lighter, the tension in the cable is going to be less. Looking at the course notes, it takes you through every single scenario that you could possibly have, and I'll just run through what's happening with some of these. So, first of all, the tension is here, and the other force acting on the lift is going to be weight. So if it is stationary, the tension is going to equal the weight. Now the weight is the mass of the lift itself and the mass of all the passengers in it. So that's what's going to cause the weight. And the tension, if we're going to just assume a single cable, these two forces must balance. No net force, therefore no acceleration. In this case, no velocity. So we're going to have okay. So that's the initial state of what's going on in the lift. Now, if we're going to go on a journey upwards, so we're going to start to move up, as soon as the lift starts to accelerate. So let's just start here. We'll just say V is going up. Acceleration. Let's just do some different numbers from the ones that are in the course notes. So acceleration up is 5 meters per second squared. It's accelerating up. If my lift, so mass of my lift, let's say 2 tons, so 2,000 kilograms, accelerates up at 5 meters per second squared. What we have is we have an unbalanced force of ME. 2,000 times 5 is going to be 10. Well, I'll just say 10 kilonewtons. So we've got an unbalanced force of 10 kilonewtons. Now remember, these do not represent the unbalanced forces. These do not represent the unbalanced forces. These are the actual forces. Unbalanced forces are kind of a resultant of separate, if you're going to say real forces. Now, what's our tension? That's what we're trying to find out here. Now, the weight is just going to be W equals mg. So we can have 2,000 times 9.8. That's going to be 19.6 kilonewtons. Right, so the force acting down is going to be 19.6 kilonewtons. However, we're getting a force, an unbalanced force. This unbalanced force is causing an upwards acceleration, so the unbalanced force must be acting upwards. If this is the downwards force, then the upwards force must be that plus that. And so we're going to have a 29.6 kilonewton force acting upwards, and that upwards force is the tension. So the tension in the cable, as it just starts to accelerate up, is 29.6 kilonewtons. As it starts moving to a constant velocity, let's just say that's 10, then forces are balanced again, so tension will equal weight. Will be 19.6 kilonewtons for both the tension and the weight. The weight will not change throughout this journey unless passengers jump out the lift. Now we've got our weight, Our weight is still going to be 19.6 kilonewtons. The tension, again, we'll find the tension. Now, if velocity is still going up, but the acceleration, let's just say, is minus 5 meters per second squared, that's going to be a downwards acceleration. So we work out the force. Again, it's going to just be ma, and we're going to have 2,000 times minus 5, and that's going to give us a minus 10 kilonewton force. Now, remember what we use pluses and minuses for. Pluses and minuses are to signify direction. If this is in the positive direction, so a minus 10 kilonewton force means that it's going to get taken off of this. The force to have a 10 kilonewton force going down that way means that tension is going to be 10 kilonewtons less than what that is. And so in this case, the tension will be 9.6 kilonewtons. Okay. Again, which is gone through in exactly in all of these three scenarios here. When the lift is traveling downwards, we're going to have a similar scenario. So as it's stationary, forces are balanced. When it's moving at a constant speed, forces are balanced again. But as it starts to accelerate downwards, remember what the first thing I said is it starts to accelerate downwards, you feel a bit lighter. As it accelerates downwards, we're going to have an acceleration of minus 2 meters per second squared in this example here. That unbalanced force, therefore, must be going down. We work out what the unbalanced force is. This, in this case, is 2 kilonewtons. Well, technically, we should have minus 2 kilonewtons there. And then we work out the tension is going to be 2 kilonewtons less than the weight, which will give us 7.8 kilonewtons in this example here. And finally, when we start to decelerate, now deceleration, so if the velocity is going down that way, in this case acceleration will be acting in that direction because it's acting against, it's a deceleration, so it's acting against the motion of the lift, and so we're going to have this acceleration, positive acceleration acting up. Our tension is going to be greater than our weight, and so therefore we're going to have, again, the same unbalanced force, and that's going to increase the tension in the cable because we're going to have this unbalanced force going up in this direction. So that's forces and lifts for you. So you don't often get asked questions about forces and lifts, and they can be quite tricky, but well, you know how to do them now anyway. Okay, thanks for watching. Bye.